Hello, welcome to another problem session. So today we are doing JEE 2024 from India, and this paper one from advanced physics paper. So we did question number 1 in a previous video. Now we're going to do question number 2. Before we go to that question, I just want to say that if you find this kind of approach interesting, you can check out my website, which is given over here. All right. So what's the question here? Well, the question is you have it's coming from magnetic field. So you have a long wire, infinitely long wire. Of course, there is no such thing physically, right? But this is ideal situation, we just say mathematical situation, and it's and on the plane perpendicular to it, this is the xy plane. All right, so this is the xy plane, and this is the z-axis, and this is piercing over there, and these are all z equal to 0 plane. So if you look at this in that plane, you are looking at a point AA over here and a point minus this is the x-axis. If this is the x-axis and this is the y-axis, there's a point over here and there's a point further out here, and you go from here to there, and on that path from P1 to P2 you integrate, from P1 to P2 you integrate B vector dot dl, and it's one of these answers. Okay, now there is a easy way of doing it and there's a hard way of doing it. Okay, so I'll illustrate both easy and hard way. Let's do the easy way first. All right, because in the exam, if you have an easy way, you should always prefer easy way. The first thing to look at is this three-dimensional drawing is all too complicated for my taste. Okay, so I will just say I'm looking directly from the direction in which current is coming at me. Okay, that's the first thing to notice. And then I've got this, so z-axis is coming right at me, so I'm going to use right hand coordinate system. So I'm going to be x this way and the y this way. So I'm looking at the plane, and point is here and one point is here. All right, so this is like a minus a square root of 3 times a, and this is just a, and this is just a, and we're going in this direction. So if you know the magnetic field from this B field is coming out, current coming out this way. So magnetic field is, let's draw them out. It's coming towards me. So magnetic field is going around like this in a circle. So it's, and so, this is like too far out. Okay, so in a circle like that, magnetic field is going this way. So if you take a path that's perpendicular, let me draw one more. Okay, magnetic field, say from here, and let's see over here, which is let me write down square root of 3a. So that point. So if we from this point, so that this is like, this distance is same as that distance, and I draw an arc. I'm going to draw an arc that goes through that point. So that's going to be a circle. So that's going to be a circle, and you can see that so in that circle you are, see, you don't go all the way there, you just go, up to this point. Don't go all the way there, and then come back here. So I go from P to Q and then to R. Instead of going P to R, if I go P to Q, and so I go P to Q to R and back to P. So if I do it in this, no current is enclosed. So on this B.dl, on this PQ, P to Q to R to P will be 0. Okay, so if you look at here, I will have I can break to P to Q, Q to R, and R to P. So this is going to be B.dl, P to Q, which is on an arc, plus B.dl, Q to R, plus B.dl, R to P, this will be 0. Now this thing dl and b will be perpendicular to each other because while b is going this way, the dl is going perpendicular to the radial. So this will give me 0 because b is perpendicular to dl on that path. So this has to be equal to just that. So B.dl, if I bring on the other side, because becomes R to P is equal to B.dl, P to Q. And you can see now here I am going in the opposite direction to what the question is saying, so I can absorb the minus sign. So this will be equal to what I need to do, B.dl and P to R. So this is what I want, and so this becomes this integral. Now this integral is all along, this is very pretty integral, all the way, which is, it's on this arc, and B is completely known, is constant. So on that is kind of B is going to be mu naught I over 2 pi this radius of this 2 pi r, and is going to be in, so B will be that, and is going to be, let's call this direction, this angular direction, minus phi hat, because phi hat will be in the other direction. So B.dl, and what the dl will be simply in the same direction I'm going, so it's also be a minus phi hat direction, and the distance will be just r times d theta. This angle, maybe this angle will be d theta. So r times d theta. So when I take a dot product with this guy, this r will cancel this r, and this will be mu naught I over 2 pi d theta. So when I integrate, this is going to be constant, and so this is just going to be mu naught I over 2 pi times the angle that's enclosed here. And you can find that angle very easily. Probably, let's redraw this picture and to find that angle. So I have from here to here, and then from here to here, we can make this angle theta 1, and let's call this theta 2. This one, this is A and A, that makes it 45 degrees, and it's all written in radian over here. So this I should have pi over 4, and this is this is square root of 3, and this is 1. So tangent that gives that angle theta 2 is 60 degrees, which is pi over 3, and add these guys, pi over 4 plus pi over 3, 7 pi over 12. So this is 7 pi over 12. This pi cancels this pi, and when I work this out, this is mu naught I, 7 mu naught I over 24. So it looks like this is the answer. So this is kind of easy way, and it makes use of this property over here, these two properties. So where does this property come from? Well, it comes from Ampere's law. Ampere's law that says in any closed loop, this was closed one, is any closed loop, you're going to be B dot dl will be mu naught I enclosed. Any closed loop is going to be like that. And this other property, I already explained this one. This property, this being 0, is simply B, whenever B is perpendicular to dl on any path, B dot dl will be 0 just from the dot product rule. And then rest is just simple like that, right? So this was the easy way. So suppose I didn't know all of this, the easy trickery method. Could I just do brute force? Yeah, you could do brute force. And let's do the brute force also. Okay. So let me clean this up and do the brute force on the next slide. Okay. Okay, so I wrote up some preliminary stuff. You can go over that. So here is a brute force method. So 2 points that I want to integrate over. It goes from P to Q. And I'm looking at a point on that path. I'm calling it A, which coordinates X and Y. So what's the magnetic field is going to be? If the current is coming towards me, the magnetic field is going in this direction. And so that's the phi hat direction. And phi hat direction is this angular, in a circle. In a circle, you have a r hat direction like that, and phi hat direction like that at that point. And if you're over there, phi hat direction is that way, and r hat direction is that way. So it varies from point to point, and phi hat is you can write down in I hat and j hat, and with that angle theta. The dl at A is going toward dx direction, so it's like that. And if I take a dot product of these two, I'll get that. And so I need to, this whole thing has to be at y equals to A. This whole thing is y equals to A. So I work out like that, and I can do a little bit more simplification here before I do the integration. So mu naught I, and from sine theta I'm going to get an A, and the 2 pi is constant, and I get a dx, and these two kind of multiply because s is downstairs. So you have x square plus a square. So if I can definitely do x, change variable, u equals to, want to get a out. How do you get a out? Well, there are several ways to doing it, right? You can put a square out, and then this becomes, and this is 1. And you can already see that if I do x over a as u, then du is going to be dx over a. So change that variable, so it's going to be mu naught I over 2 pi a square. You probably have your own way of doing this, and that would be okay. So this is a over there, and the dx is a du, and you have a u square plus 1. So this is b dot dl at an arbitrary point. So we need to integrate from point P to point Q, point P to point Q. This form informal, right? I don't have an actual variable there, and this from point P to point Q I'm going to do. So you can see the a square all kind of cancel out over there, and so this is just basically mu naught I over 2 pi arctangent u, and from P to Q. So u is x over a, so mu naught I over 2 pi arctangent x over a for point Q. So x over a for point Q is 1, and then minus arctangent inverse of u at point P, and point P that's minus square root 3. So this is minus, pull over there, that becomes plus, and this is pi over 3, and this is pi over 4, and you can see that this brute force method gives me same thing, 12 and 7 pi, which is same thing as a. Okay, so that much. That's a lot of work, and I kind of like the previous method because it used a couple of interesting results from Ampere's law, and how you a B field is perpendicular to the path you are integrating over, it gives you 0. So I prefer that method, but if you can't figure out that method, that's okay. You can actually do this problem even straight from the magnetic field of the infinite wire. Now this formula, you have to memorize it, because this is so useful. But if you don't memorize, you can derive this even in the context of a test by using Ampere's law, okay, which I'm not going to do here now. All right, so I'll see you in another video. Bye.